All right.
Is it being challenging?
No, it's just there's just that delay. So you get the start the stream and then the preview the stream, but then to actually make it go live on YouTube, it takes just that extra second. And I am not a patient man. So, oh my god, I've made a terrible mistake. Hold on. We're live, by the way.
Okay, I'm curious as to what exactly this terrible mistake is. Ah,
Here we go. I always, I always tell guests when we interview them, like, you must always, always have a copy of your book ready to go at all times. That is just that's self promotion 101. So, yeah, and I did because I gave one to my parents.
cool.
Yeah, how awesome was that? Um, but now I've got a replacement right here. This wonderful book. Uh, oh man, people are still waiting for it. Yay! A copy arrived. Was that the one? Did they send you one, or is that the one that went to CosmoQuest?
This is the one that went to
Oh,
CosmoQuest.
great!
It arrived today.
Wonderful. Um, do you see your picture in it?
Not yet. I opened it just in time to have it out of
Oh,
its
good.
envelope.
Awesome. So
In
I got
fact, the
today.
envelope is on the floor somewhere to get it off camera.
Yeah, just amongst all of the Amazon packages that just float around your house.
We're getting better at
Are
that.
you?
We're
Yeah, it's like a
trying to get better at that.
yeah. I've really cut back our Amazon usage now. Like I think when everyone goes like first gets their like Prime account, it's like magic. And they're like, I can't believe it. I order a thing and it just shows up, and then after a while you're like, I don't need any of this stuff. And so you just only when something like literally breaks, you replace it. But apart from that, I've definitely decreased the number of doodads and gadgets that show up in my house.
Your shelves are getting fuller and fuller every episode, however.
Well, it's all these books. They keep sending me books. I use the new ones to go in. What I actually do is I try to promote it, and then I usually donate the books to my local library.
That's cool.
My Nancy, your lighting is really low. It is really low, and that's sort of set. I sort of reconfigured the lighting for the virtual star parties, and so it's sort of because people had complained that the lighting was way too bright because it was like dark sky and these objects, and then really bright pictures inside of it. So we configured the lighting. So the thing that I have to do, the lighting on me is actually really good, but I have to now light the background so that it balances out. So have we shared our glass awards? I
Mine
don't.
is on my desk at work, so I can't grab mine.
I'll grab mine.
Okay.
All right. So I feel like we showed this off, but if not, check this out because now it's sort of just reflection. So this is the folks who organized the Astronomy Cast 100. 500,
500.
sorry, made these really cool glass awards for Pamela and I. And how cool is it? So this was from the Weekly Space Hangout crew. And then the other thing that I've kept on my desk because I've been meaning to show it off, and I'll go full screen Fraser on this one. Um, is so this was the shirts that they did for Astronomy Cast 500, and then they all signed it.
Yeah. Mine is downstairs in the
How
dining room.
cool is this? Let me just go.
He is so much better at putting stuff away than I am.
I don't know. That scrolled through. How awesome was that? So thanks everybody. That was amazing. Um, it felt very loved to be
Yeah.
amongst all of the people that were there for the 500th episode. It was a party. It's so funny. We always spend so much time all apart, right? We're all just scattered across the whole planet, and it's important to
Yes.
to meet in real life as human beings. And I think it's something that we don't put enough of a emphasis on. And then whenever we do meet up people in real life, you're like, oh yeah, people rule. So anyway,
Yes.
that's all I have to say about that. And we're actually going to be hanging out in about 2 weeks at ThinkerCon. So
Yes. Where we get to have dinner under a Saturn V, and all of you are invited, but it's not free.
no, but if you go to ThinkerCon, you can find out about it. All right then. I'm ready to start recording if you're ready to start recording. Now we have to cut things quick. Pamela's list of to-do items is gigantic, and she's just getting out the door or just got back from TwitchCon, and now you're out the door again.
Yeah. So I'll be at Sound Education this weekend, which is a podcasting conference. So podcasters, come say hi.
Where are you going to be? Sorry?
It's up at Harvard University. It's Sound Education.
Awesome. All right. Tell me when you're ready.
I am pressing record. It is not using the correct microphone.
No. Mine is.
Audacity.
Although still, I struggle with microphones, making them sound good.
Yeah. Okay. It is now using the correct.
Excellent.
But my fish tank is on. Let me turn that. Sorry.
I'm gonna stop my recording.
I suck. Okay. Turning off fish tank.
Okay. Hello to Joe Cottle and Jorge Schwann and Tom Van Scotter and Gordon McLennan and Paul Gracie and Phoenix Torres and K Spence 303 and Bill Sugden and Johnny Zed and Nancy Graziano, Ben Kalo and Jason Elric and David Reynolds and Coffee Singularity, Amanda Pita and Harry Patrick. Did I say John Suffield? Magnus Thymer Jensen, Gordon McLennan, Tori Gadwa, Adam Synergy, good old Nightbot, Chris Adams. All right.
Okay. I've turned off the fish tank and the space heater.
Excellent. You and your fish will get very cold over the next 30 minutes. Here we go.
Yes. Okay. We are recording.
Right on.
With no background noise.
Okay, great. Here we go. Astronomy Cast, episode 504, Radar, Lidar, and Sonar. Welcome to Astronomy Cast, a weekly facts-based journey through the cosmos where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Great. The ongoing relentless book promotion continues. Thanks to everybody last week who listened to my sad pleas and went to Amazon and gave us some ratings. We now have 15, which is amazing because before it was zero. Literally this time last week we had 0, and it was the weirdest thing. A top-selling book, but still 0 reviews. So now we've got some. So again, the book, Universe Today's Ultimate Guide to Viewing the Cosmos. And I want to let you all know that I'm happy to show up on anyone's podcast, anyone at all, for any purpose whatsoever, and be interviewed and shamelessly self-promote the book with David. So if you want to have me as a guest, just let me know. Just send me an email, fraserkane@gmail.com. All right, let's get on with this week's... Oh, Pamela, how was TwitchCon? Quickly.
TwitchCon was fabulous. Massive shout out to all the other podcasters that are part of the Brain Bites team and to the good folks at NASA Silicon Valley Podcast for hosting the event. You are all awesome. Check us all out at I'm Star Strider. Check out CosmoQuest at CosmoQuestX, all on Twitch, streaming all the time.
I lurked a couple of times to watch some of the live shows that happened. The big panel with you and Skylius and Scott and a whole bunch of people were there, which was great. Probably an archive exists somewhere out there. To really study something, you want to reach out and touch it, but what can you do if you're separated by huge distance? You reach out with electromagnetic or sound waves and watch how they bounce back. Thanks to radar, sonar, lidar. Now, Pamela, we have already done an episode all about radar, So this is going to be sort of a version, but just to let people know, we're not crazy. We didn't forget. We remember everything always. But uh, but there's more to the technology than just bouncing radio waves off something and seeing how they go back. So, but let's do a bit of a recap. What does this suite of technologies share in common? How does it work?
Well, in all three instances, we have some sort of a wave, whether it be a sound wave, a light wave. We have a wave. We are shooting it at something and then listening for the wave to come back and listening to hear how the wave has been changed. And the cool thing about this way of doing things is waves in some cases will permeate to different depths depending on the thickness of a material. And this allows us to get a three-dimensional understanding of the density profile of the things that we're looking at.
The density profile. So, I mean, I sort of got this concept of the shape, and I've been, let's see, I'll give you an example. I was actually, as a little kid, with this ferry that used to go back and forth from the island that we lived on, and the ferry captain knew us and would let me come up and actually help pilot the ship. I hope no one finds out that I was their captain occasionally. Um, but but they had a radar system, and I was fascinated by it because it was this amazing thing where you get this sweep around of this of the radar system that was turning overhead, and you would see it map out the shape of the boats and rocks around you at all times. It was this fascinating technology, and you could see the blobs, the dots on the radar map would then map out to objects that you could see around you, like that boat over there or that rock formation or whatever. But but it was always, you couldn't see inside anything. It was just this shape, and you could. So that's sort of what I always thought radar and lidar and all these things were used for.
Well, sometimes you get lucky and something is partially transparent to the waves that you're looking at. One way to think of this is if you have sunglasses, not all of the rays of light from an object make it into your eyeball. Many of the light rays get reflected off. This is why it's so easy to see yourself reflected in somebody else's sunglasses. So with sunglasses, you have a surface that is partially transparent, partially opaque, thus only part of the light gets through to your eyeballs. Now, with different kinds of materials, you have different proportions of the light transferred, not transferred. With sonar, you have different portions of the light transferred, not transferred. This is how, when you look at a baby in somebody's stomach using a sonogram, you are able to look through the belly and reflect light off of the baby. And in this case, you have some of the sound wave transmitted, some of it reflected off by the different fluids in the belly, by the baby, and all of these different things make a really noisy image. The computers can translate into this is something with girl parts, or this is something with boy parts. Uh, and we're kind of lucky this way because when it comes to light, you can do even more interesting science where nowadays we're reflecting light off of forests. And while we see the canopy reflecting back some of the light, but we also see some of the light making it through that canopy of trees and sending us back information about, well, hidden cities that are lurking within those rainforests.
Well, I'd like to talk about some of the kinds of research that's been done with this technology, and then talk about which wavelengths are being used and how they're being bounced. So there's a few that are absolutely spectacular, and I think one of the best examples of this is the work that say Cassini did trying to explore Titan, which and there's this kind of ironic story when they first sent the Voyager spacecraft to Titan, they specifically made a flyby with the Voyagers to get a close-up look of Titan, and the problem is Titan's thick atmosphere completely obscured all of the views that it was going to be able to get, and so it just got views
Orange
of
blob.
orange blob, yeah. and sadly, and so it took Cassini with a way to be able to see through those clouds to be able to reveal the surface underneath.
And in this case, it's really cool how they're using it with these technologies that require a surface to reflect light off. We are able to look at Titan and go, here be liquid, look at how smooth and reflective it is. Here be ground, look at how not smooth and not reflective it is. And the radar that they're using penetrates through those clouds, no big deal. And we are able to get returns on what is the surface. This is very similar to the Magellan mission, which radar mapped out Venus, another one of these cloud covered, who knows what's down there kind of worlds where we drop probes and they die almost instantly. Well, in this case, radar allows us to see through those clouds and get an understanding of these surfaces.
And so Cassini was equipped with a radar system. It as it orbited or as it did its flybys of Titan would send these radio chirps at Titan and then watch how these radio waves bounced off of the surface of Titan and then be able to know the difference between sand made of ice and seas made of liquid methane because of the smoothness.
Yeah, and this is something that relies on comparative planetology. We actually use radar mapping of our own planet with satellites to trace out where are there icebergs, where is there glaciers moving at this rate or that rate. While we all prefer, or at least I think most of us prefer, to look at the shiny pictures that are taken in optical wavelengths that our eyeballs are used to. Spacecraft are out there using, well, less pretty pictures to keep a more automated and scientific view of our surface. So with radar, we are able to track those icebergs. We're able to track the progress or lack of progress of ice sheets. And we're able to see how things freeze and how things, well, thaw out over time.
And so you already moved on to the next thing that I wanted to talk about was this mapping of Venus, and that again is just absolutely stunning because until the Magellan spacecraft went in the 1980s, we had no idea what the surface of Venus looked like, except it probably sucked, right?
Well,
but
that,
but were there
for
ancient
sure.
were there ancient continents? Was there a lot of volcanism? Were there asteroid impact scars like we see on the moon? Could we see evidence of oceans that had boiled away a long time ago? Things like that. And so,
And we literally had no idea of what the surface of Venus was. We assumed rocky object based on our understanding of its mass, based on, uh, well, it seemed like the right idea. Essentially, it was much more scientific than that. But, but we'd sent a variety of probes there, and none of them were able to give us a worldwide systematic understanding of what was going on. So when Magellan went up in 1989, it it started giving us detailed understandings that fundamentally changed how we look at things like plate tectonics. One of our core understandings about our own planet is that we have a variety of plates that float atop a molten core. And as these plates pull apart, new land is formed. As they duck under one another, we have land destroyed. And along the ridge lines between the plates, we have active volcanism. We also have hot spots with active volcanoes, but those are different science. We kind of assumed that worlds were likely to have this kind of plate tectonics if they had a liquid core, but we didn't know if Venus had a liquid core or not. And even if it did, if it didn't now, it would have in the past. So, how did this affect its surface? Well, in studying this world that turned out to have volcano after volcano after volcano after volcano, all apparently dead, spread across a surface that didn't have all that many craters when compared to like the moon and Mercury, seemed for the time not too extraordinarily different from Mars, but it was different. Um, how did we explain this? And it built up this, oh, expletive, we have to change our understanding of plate tectonics to include this idea that you can have a worldwide recycling of the crustal material almost all at once
Yeah.
with this massive explosion of volcanism worldwide. And that all came from radar.
Yeah, and we're completely now going down the rabbit hole, but that idea that the surface of Venus turned itself inside out in relatively almost no time. It just churned upside down is one of the most mind-bending concepts in planetary science that I have ever sort of learned. So let's go back then and let's talk about the technologies then. So radar, lidar, sonar, what's the difference?
Radar uses longer wavelengths of the electromagnetic spectrum, which includes X rays, gamma rays, the optical light, visible light that our eyeballs see, infrared, millimeter wavelengths, radio wavelengths. So here we're starting to look at radio wavelengths. Exactly the length that we're looking at is going to depend instrument to instrument. If it's called radar, it is redder than what our eyeballs can see. So here we're starting to talk in general millimeter and longer wavelengths. With LIDAR, it's a stupid name. This one kind of bothers me. It is referring to visible light, the stuff our
Lasers.
eyeballs see, and they just call it light for LIDAR, whereas with radar, it's radio light. So LIDAR starts to use visible colors of light. This is, think of lasers like we are used to using to play with various cats, rats, dogs, whatever. Imagine those kinds of devices being used to reflect laser light off of another world and measure the light travel time. Um, so with sonar, now we're getting on to sound. In this case, we're using sound waves to penetrate through a medium that is capable of conducting sound. So with sonar, it's not like we're using a satellite to do it, but with sonar, this is the kind of thing that we're really looking forward to be doing in the future, because we know the power of doing it here on Earth to trace out ice sheets and the cavities beneath them and the lakes that form within them.
So there's some interesting. I mean, we've talked about some other worlds, but of course, these technologies are most used here on Earth. Many spacecraft, Earth-observing spacecraft, are equipped with different flavors of these technologies. Sometimes many of them all at the same time. So,
Yes.
what are some of the different kinds of things you're going to be looking for, and then which spectrum are you going to be using to do with?
So let's start with lidar. So with lidar, the colors that get used depend specifically on what's being looked at. We had MOLA and LOLA data that was taken of Mars and the moon, respectively. And here we're looking at wavelengths of light that are similar to what our eyeballs are able to see. Um, and they tune it on Earth depending on the problem. One of the most fascinating things to me about what they've done with LIDAR on Earth is they actually for a while used it to hunt down drug dealers, where they tuned the color of light to specifically match what would get reflected by different kinds of plants. So by looking to see what got reflected, they were able to say here's where the pot is. So yeah, different leaves reflect very specifically different shades of color. They absorb and emit slightly different shades of infrared. Um, Yeah.
Right. But you know, an example. I don't know if you've been tracking this, but NASA's, the European Space Agency's Aeolus mission, which is designed to search for wind, is equipped with a ultraviolet lidar system. So,
Yes.
right, and so you really will use in the lidar. You really use that whole spectrum. You go from the infrared through the visible through the ultraviolet, and so different things are going to be, as we mentioned, are going to be reflected, absorbed, bounced in different ways depending on which of those wavelengths you choose. And if you've got a very specific mission that's looking for just ice or just measuring water levels, or as you said, measuring certain kinds of plant growth, you want specific wavelengths for each one of those kinds of missions.
And with the Mars mission, they had it tuned to just redword of what we can comfortably see. And that was just because that was the color that they knew that they could get the best reflectivity for the kind of science that they were doing.
So, what are the downsides then of these various technology? I'm assuming they take a lot of power.
Well, they take a lot of power. They're each susceptible to different limitations on what they're able to see. So, with the LiDAR program, what you're looking at is you're firing lasers, and a lot of that light isn't going to get reflected back. Let's face it, when you have a really rough surface that isn't, well, a liquid ocean or solid ice, most of the light gets scattered in a random direction that is not the direction that your spacecraft happens to be located in. And and so you don't necessarily get the kinds of accuracies you might want. You don't get the kinds of resolutions you might want. So, right now, as much as we would love to have a detailed map of the moon's surface elevation using LIDAR that had the same resolution as our optical images, where we're looking at each pixel covers a half meter of surface, we're instead looking at each pixel in LIDAR is many meters of surface, and that smooths out any measurements we have. It hides the boulders, it hides the tiny craters. This kind of a limitation is one of great amounts of frustration when you're trying to do detailed maps, because with LiDAR, we'd be able to very quickly develop crater maps that we just can't do otherwise. When you're looking at radar, again, you have power constraints, and here you have wavelength constraints as well. So you can only see things that are, well, bigger than the wavelength of light that you're using. Otherwise, the stuff is just invisible, essentially. So early on, we used radar to actually measure the distance to Mercury, measure the distance to Venus, and that's awesome. But if you're off in the distance to Venus by a matter of many meters, cool, who cares? If you're trying to measure the height of that mountain you're trying to land on, that's going to matter. So
Right.
again, it's a matter of resolution. With sonar, where you start to get into frustrating constraints, is you have to have a medium that sound can transmit through, and you have to be trying to measure something that sound can reflect off of. So here we're able to use sonar to measure different densities in soil, different densities in ice, to measure out the size of cavities under uh, glaciers. Again, you're going to be limited by the size of your wavelength. So, sound waves, it all comes down to you can only measure things that your wave can reflect off of instead of passing through.
One mission that's in the works, and the inclusion of a radar system was actually a bit controversial, and that's the Europa Clipper. But
And
boy, is it going to be great if it works.
yeah, and this is one of those things where spacecraft remain dead to me until they're
Of
finished.
course, of course.
Because the
James Webb.
question the question becomes, um, what instruments actually will launch. Over the years, we've seen many spacecraft that had instruments added and subtracted over time. And here we're looking at a mission that is still many, 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 many years away. So um, stay tuned. Stay
But
tuned.
let's but we should just mention briefly what it's going to do. Come on, I get it. It doesn't exist. It's not it hasn't launched, so it's dead to you, but the idea, like, the whole idea of the Europa Clipper to be able
Yeah.
to scan under the ice sheets on Europa to try and sense how thick the oceans are down to a few kilometers down is a great idea, and something that astronomers would really love to know the answer to.
And here I'm actually going to say that what we're worried about, I'm not worried about. The people who are most excited are the glaciologists, the hydrologists, the people that study worlds that have ice. It's the folks who study ice sheets here on Earth that have allowed us to make the best breakthroughs in our understanding of what is it that allows Europa to act and behave and have these ice sheets that we see on it, and what we've learned from using radar and sonar here on Earth to study our world's ice sheets to find massive lakes under the ice. And the same technology that tells us where our own glaciers' subsurface lakes are, this is the technology we now want to use to find out how thick is the ice on Europa and can we get down to the liquid water.
And the big controversy, and this is why I want to I push back against your non spacecraft launched ban, but is the fact that even getting, like, it's such a power hungry instrument on board
Yeah.
the mission. They could have had a lot of different science experiments that they could have put on this mission, and in the end they went with something that's going to be gobbling up a large chunk of the power that's available to the spacecraft. Is this ground penetrating radar system that they're going to be using? So it paid, people who advocated for it knew that they were going to be literally having to steal from other science that the mission could have done.
And and it is very frustrating, but at the same time with work that's being done here on Earth, ground penetrating radar is what is allowing us to find Viking boats buried in cemeteries, to find, in combination with LIDAR and other remote sensing techniques that are, again, all power hungry reflecting techniques to map out cities on in deserts, cities under rainforests that have been abandoned for centuries. We know that this is a powerful technique that is revealing things on our world that regular satellite mapping at high resolutions never revealed to us. So it's this trade off of, we know what science is possible, but expletive, we wish we could have all the missions, all of them, and do for other worlds the same myriad of multi-messenger techniques that we see here on Earth.
Yeah, and I think that's really the key, is that a lot of these technologies are used all the time, especially down here on the ground, or to observe the Earth itself from space. But to be able to get that kind of technology to another world, to be able to do that kind of exploration there is the great challenge. And turns out space is big, and getting things to other worlds is a rough time. And when you deal with all the power constraints, I mean, you look at Juno, it's using solar panels. The solar panels are, I think, 25 times as much solar size to be able to get power. So essentially 1/25th the power at Jupiter than you would get at Earth, which is terrible, right? You have to have
Yeah.
gigantic solar panels to get a tiny amount of power. You're going to have a similar situation with the Europa Clipper, unless they decide to switch to an RTG. So
We just have a limited number of RTGs because we haven't been doing a significant production here in the United States.
make more
So,
nukes. I can't believe I'm saying this, Pamela, but you
well,
Americans should
not
make more
nukes, make
nukes.
more nuclear materials. We need more
Right. Of
nuclear
course.
materials. There's a
Yeah.
difference.
No more nukes. More nuclear
Yes.
materials for peaceful exploration of the solar system. Awesome, Pamela. Well, I'm excited about the future missions and the work that's being done here on Earth using these technologies, and we will talk to you next week.
Sounds great, Fraser. And now we save.
504. Feels like it'll be forever now before we cross another episode. Big number.
Yeah.
We'll toil away in the 500s for 2 years. 3 years. All right. Okay, I'm safe. Can I hit you with like 2 questions?
Yeah.
All right. Larry Beckham says radar seems to be the way to go to image near Earth objects. Why does it beat optical images?
So it gives us two different kinds of information. And one thing to think about is radar is like hitting something with a flashlight. So if there's an asteroid flying by, we can only see it in reflected sunlight. If there's an asteroid flying by, we can also shoot radar beams off of it and illuminate the crags, the recesses with that reflected light and measure the reflectance. So it's the difference between trying to see something in a dark room that is just kind of sort of reflecting light and you can't really figure out uh, the details versus shooting something with a flashlight. In this case, just a radio flashlight.
Right, right. So you're shining a really bright light on the rock as it flies by, concentrating a tremendous amount of energy on it, and then seeing as much of those photons that will bounce off of it and return, which is different
Yes.
than just how the sun will illuminate it as it flies by. Both are useful, but it's those close approaches when that radar really pays off, and that's why it's really
Exactly.
just done when a rock flies within some distance of Earth. And this comes from Jason Elric. At what scales will you have to factor in general relativity when making electromagnetic spectrum measurements?
Uh, so the word scales on that is giving me a bit of pause because
I mean, you
it's
have to
not.
calculate the travel time from your
Yeah.
emission to when you receive the signals back.
Well, and it gets so many different things play into it. So there's you have to use general relativity just because of the gravitational redshifting between space and the surface of the planet for calculating time with GPS. You worry about uh, expansion in the universe when you're looking at light travel time for things that are particularly big. But these aren't the kinds of things where you really take any of it into account with radar and lidar. Um, so in general, radar and lidar aren't things where GR plays a strong role.
Right, right. The speed of light definitely does, but
Yeah.
but the speed of light goes the speed of light, and
Yeah.
so you don't have to really worry too much about the relativistic side. You just know that you have to shoot. But I guess it's like a bit of his targeting, right? Like when you shoot at something that's kind of far away, like say you're going to shoot your radio waves at Mercury, which is something that they tried.
There is a relativistic correction for figuring out where the heck Mercury is located.
Where Mercury is located. You know, you're
Yeah.
not going to shoot where Mercury is in the sky. You're going to shoot where Mercury is going to be when the light waves arrive from your telescope, although it's not that far because it's only been
Yeah.
eight
It's
minutes,
less
right?
than 8 minutes
Yeah.
away and not moving that fast in the grand scheme of things compared to how the beam is going to expand as it travels through space.
Yeah. All right. Well, that's all the time we got. Sorry, everybody. Pamela's got to run, but
Sorry.
it was great to at least sneak in this episode before you do some travel. Have a great trip. I travel tomorrow as well, so I'll have
And
a
we will both be at ThinkerCon and we'll try and do some recording while we're there.
perfect. And if you're going to be there with us, come eat dinner under a rocket with us. All right. We'll see you all next time.